Hey guys, today we're going to build a neural network and use it to predict whether or not it's going to rain tomorrow based on some real world weather data. Let's begin by having a look at the data for it today. The dataset is actually hosted on Kaggle and it's called Rain in Australia. So the most important or the task that we're going to do is to predict whether or not it's going to rain tomorrow. As you can see, the data is about 14 megabytes and I've already prepared the data and uploaded it to a Google Drive. So it should be a bit easier to download it and have a look at it. Let's start by opening a Google Colab notebook, and just for now, I'm going to ignore this. I'm going to check the runtime that we're going to need a GPU for this lesson. And I'm going to go to a new cell right at the bottom in here and start by just getting the data. I'm going to copy and paste my Google Drive ID and I'm going to use gdown to download the CSV file. We'll have to wait for the GPU runtime to connect. And after that, you can see that the data is being loaded and we have a CSV file weather.os.csv on our machine. And you can see it in here as well. So the first thing that I'm going to do is to read the data into a data frame. Okay, so this should do the trick. But yeah, I forgot to do my imports. So let me copy and paste those. And I'm not going to go over each and every one of those. But yeah, you can see that we are importing pandas, numpy, seaborn, and PyTorch in here. So let's load this. And we are also setting some random seeds. So next I'm going to load the data frame. And after that, I'm going to have a look at a couple of rows of this data frame. And as you can see, this data set has a lot of features or a lot of columns in here. And we are also seeing that some of the values are actually missing. So this will be a problem. And we have mostly columns that contain just numbers, but we have this, for example, the location or the date and the wind direction, which seems to be either strings or some sort of dates. And for the rain tomorrow, we have no and maybe probably yes. So we'll have to convert those to numbers as well. And the rain today should be converted to a number as well if we are going to use it to predict whether or not it's going to rain tomorrow. So let me start by just looking at the shape of this data frame. And we have a lot of data points and 24 columns. We have roughly 140k examples, but after some pre-processing, I'm going to have a look again at the shape of the data frame after we're done with the processing itself. We've already seen that some of the data is missing, and that this is a problem for our model. Another thing that we saw is that we have some strings in columns, and neural networks can only work with numbers. So we have to do something about this as well. And the last thing is that our data frame contains 24 columns, which is a bit too much for us to wrap our heads around building a simple model using this data frame. So I'm going to begin by first checking how many missing values are there in each column. And I'm going to use isNA and sum the values for each column. And as you can see, rain tomorrow has a zero NAs, which is great. But rain today has some. The date and location also don't have any zeros. And most of the other columns contain some missing values. So the next thing that I'm going to do is create a subset of the columns that we are going to use for prediction. And basically those columns are selected via using correlation analysis, using some statistical methods. But for the sake of the simplicity, I'm going to say just we are going to use those, and I'm not going to explain how we come up to this. If you're more interested in feature selections, maybe I'll do a video on that in the future. So let's say that we are going to use the rainfall column. We have humidity at 3 p.m., the pressure at 9 a.m., whether or not it rained today, and finally the value that we're interested in, rain tomorrow. And our new data frame is going to be data frame that contains only those columns. And if I have a look at the head of those, we're going to see that we have just this subset of columns. The next thing that I'm going to get rid of is those no's and probably yes in here's. So I'm going to convert those to numbers, and we are going to assign 0 to no and 1 to yes. So to do that, I'm going to replace the rain today column, and I'm going to replace the no's with 0 and the yes with ones, and I'm going to do this in place, and I'm going to do exactly the same thing for rain tomorrow. So yep, I have a syntax error. Well, this should hopefully be it. If I have a look at the data frame now, you can see that we have rain today 0 and rain tomorrow 0. So some of the values in here, as you can see, are floats, which is a bit strange. Let me just go and rerun this, so to make sure that everything is running okay. Yeah, rain today still is a float, but yeah, we will continue and handle if when or even if this is a problem. So the next thing that I'm going to do is to basically drop every row that contains even a single column with a missing value. So this is not the best way to handle the situation, but for the purposes of this tutorial, I'm going to just do that. There are other more advanced ways to handle missing values, and I'm going to link some of the resources that I've checked out and some of the tutorials that I've already written previously, so you can maybe handle the situation better when you're doing some practical task. So I'm going to just drop every none, and I'm going to have a look at the final data frame, and again I'm going to check the shape of this. We've only lost around 10% or even less from the data, which is great. And we have now only 5 columns that we are going to use. And recall that we are going to use only the first 4 columns to predict whether or not it's going to rain tomorrow. So let's have a look at how many of the examples contain that it's really going to rain tomorrow and how many of those contain that it's not going to rain tomorrow, which is really important for us. And this is pretty bad because we have a lot of examples in which it's not going to rain tomorrow, and only around 1/4 or even 1/5 of the examples contain rain tomorrow. So let me just show you the percentages of those values. And yeah, almost 78% of the data contains examples for not raining tomorrow. And this is a huge problem because you need to have enough data from each class. And the first class is not going to rain and the second class is going to rain. So you need a roughly even amount of data for each class, so your model actually understands the features of each example or each class, so you can actually predict better. And this problem is really well understood, and it's very often that you can see this problem when you're working in the real world. There are again a lot of ways to handle this. Some of the oversampling and undersampling tasks you can do. I'll also link a reference to this in the tutorial. So about some ways you can use, some methods you can use to handle this situation. But just for now, I'm going to continue and skip the problem whatsoever, which is not a great solution again. And you're going to see why our model is going to suffer from this class imbalance. And another thing that you should note is that if you are just building a model that answers that it's not going to rain tomorrow every time based on this data set, you're going to be right around 78% of the time. So this is really bad thing again. And we need to build a model that is going to be at least this accurate to consider it that it's just even a bit useful. Okay, so the next thing that I'm going to do is to create the features using the data frame. I'm going to select a subset of the columns that we're going to use to predict whether or not it's going to rain tomorrow. And I'm going to extract the labels or the target variables, the y's, which is going to be the information that it is going to rain tomorrow. So to do that, I'm going to take a subset of the columns, rainfall, humidity, rain today, and pressure at 9 a.m. And for the y's, I'm going to subset only rain tomorrow. Let me execute this. All right. And the next thing that I'm going to do is to use the train test split to create a training and a test dataset. We're going to use the training dataset to teach our model the examples about how it's going to rain or not going to rain tomorrow. And we're going to use the test dataset to basically evaluate the performance of our final model. And let me go to another line in here. Train test split comes from scikit-learn, and it accepts the features, the labels, and the test size, which is going to be, in our case, we're going to reserve 20% of the data for the test. And I'm going to use the random state to make sure that this split is reproducible by you. All right, so if I check the shape of the training data, the training features, we have the 4 columns and we have roughly 100 examples in here for training. And if I have a look at the first couple of examples, you can see that we have some data, and these are the features that we are going to use to predict will it rain tomorrow. Okay, so the next thing And final thing about the data preprocessing step is going to be that we are going to convert all of those arrays, NumPy arrays actually, or maybe, those are actually pandas data frames. We're going to convert those to torch tensors. And we need to do that because, well, we're going to use PyTorch, and PyTorch is working with PyTorch tensors. So let's start by converting the X train. And we're going to convert it from NumPy. And I'm going to convert the data frame to NumPy. And I'm going to convert all of this to a float tensor. I'm going to do exactly the same thing about XTest. Next, I'm going to convert the Y train. And actually, I'm going to remove an extra dimension that the Y train currently has. Because if I show you right now, the shape of Y train is around 100k, and we have one extra dimension in here. Maybe this is because, let me check actually this. Okay, so this shouldn't be necessary. I'll fix this. I'll fix this later in the tutorial. But yeah, let me just stick to this, and I'm going to remove the extra dimension in here. I'm going to do exactly the same thing, torch from NumPy. I'm going to convert Y train to NumPy. And I'm going to convert this to a float. And exactly the same thing for Y test. So let me execute this, and let's just check the shapes again, because probably the most important thing that you must do while preparing or pre-processing your data is checking that everything is still in the correct shape. So yeah, we have the exact number of rows in the X train and Y train, as you can see, and we have 4 features in here and only one feature, the target variable, which will be that it's going to, whether or not it's going to rain tomorrow. Finally, we're ready to build our first neural network. So let me begin by writing it out. And building a neural network with PyTorch is really simple. You just have to extend, or at least one way to do it is to extend a Torch NN module and define your model in there. And our neural network is going to accept the features, these 4 columns, rainfall, humidity, rain today, and pressure, and it's going to output a single value that is the likelihood that it's going, or how much confidence does our neural net has that it's going to rain tomorrow. So let's begin by starting and writing this neural net thing or class. But first, let me just say a couple of things about neural nets and why neural nets are so cool and so popular these days. Well, it looks like neural nets are pretty much dominating almost all tasks in machine learning, statistical learning, deep learning, or whatever. When you talk about natural language processing or image computer vision, you can see that almost all state-of-the-art models are performing some neural network, are using some neural networks. And it's really cool to see that something that it's been mostly a theoretical thing in the 90s or the 80s is now just state-of-the-art, very practical and working models that can do almost any task. And one of the most important qualities or features of neural nets is that they can actually estimate or approximate any function you can think of. And this is mathematically proven using the universal approximation theorem. And the theory behind that is very convoluted, but yeah, you can see if you're more mathematically inclined and have a look at the paper that I'm going to link into the tutorial. So let's start by building a neural network with PyTorch. So let's start by creating a class, and I'm going to call it net from neural net, of course. And in here, I'm going to, again, implement the torch or extend NN module from torch. And in this class, we're going to do two things. We're going to define a constructor. And in this constructor, I'm going to define a couple of layers. Neural nets are basically graphs, but their nodes or vertices are actually aligned as layers. And we have an input layer, we have hidden layers, and we have an output layer. The input and output layers should be pretty self-explanatory, but the hidden layers is where the magic happens. There are every vertex in this type of graph is called a neuron or a node, and each neuron has its own numerical value, and this value, you can think of it as a knob. This value can take different numbers, different numbers. And based on those numbers, your neural network is going to predict whether or not it's going to rain based on the features that are passed in as an input. So we're going to create a couple of layers. We're going to basically stitch them together and create a graph. And the output of this graph is going to be the confidence or the likelihood that our model thinks that it's going to rain tomorrow. So let's begin by creating the constructor. And the only parameter that our constructor is going to take is going to be the number of features. In our case, this is 4, but let's build it a bit more generically. I'm going to call the super constructor or the parents constructor in here. And then I'm going to define 3 layers for our neural net. And those layers are going to be nn.linear or fully connected layers. And each of those layers contains in features, the number of input features and output features. So we're going to start our input layer or FC1 as number of features. And then I'm going to specify that this layer is going to have 5 output features. Then I'm going to specify another layer. And in here, I'm going to specify again 5 and 3. You must basically match this number with this number when you're building neural nets. So let's go to the third layer. And this will be the final or the output layer in here. And in here, to match this value, we will have to put in 3. And the output is going to be just a single number, the degree of belief that our model thinks is going to be raining tomorrow. So this will be just 1. Okay, so the next method that I'm going to define is the one that is going to basically use all of those layers, and this should be, or it's a bit of a special method in PyTorch, and it's called forward. And this method again will take just a single parameter, which will be x, and x is going to be the data or the inputs of our model. So the thing that I'm going to do in here is basically flow this x through each layer. And after each layer is called, I'm going to take the input of the previous layer, output from the previous layer, and use that as an input to the next layer. So we're going to see something a bit special in here as well. So the first layer we're going to do something called frelu, and I'm going to explain what this is in a bit. And I'm going to apply the first layer on X. So we have some result after applying the first layer. I'm going to copy and paste this, apply the second layer. And finally, I'm going to return the result using torch.sigmoid, which I'm going to explain in a bit as well. And the result is going to be the application of the third layer, given the input from the previous layer. Okay, so let me execute this. And this is your first neural net. It's really simple. And you might ask yourself, well, how did we choose those numbers? And those numbers are actually going to be the hidden parameters or the knobs that our model uses to predict whether or not it's going to rain tomorrow. And the short answer to this is by trial and error. And there are some approaches that are just a bit smarter than trial and error. But in general, when doing those things in practice, you're most likely not going to build a neural network from scratch like the one I'm showing you here. And you'll probably use some bigger model which already has some predefined architecture, which might be very well optimized. So you don't actually need to care too much about how you can define this neural network architecture. So let's continue by creating an instance of our model. And recall that our model expects the number of features. And the number of features is going to be the shape of the column numbers from our xtrain, because this will be just the number of features. And I'm going to call a function that I've already defined, which is ANNVis. So let me go to the top of this and execute the cell. Next, I'm going to show you, the neural net that we've just defined. Okay, so let me just go ahead and show you the code for the ANNVis. And this is basically just a tiny rewrite on this Python library, which is done by Prodicode, Tudor Georgiou, probably. And thanks, man. This guy did this neural network visualizer for Keras. So I just went ahead, deleted most of the code that is based on Keras, applied some PyTorch code and a bit of styling. I've changed the colors and whatnot. And after that, you can get this, I think, very good looking graph or visualization of your neural net. And in here, you can see that we have the input layer, which contains the 4 features that we're going to use. We have the output layer, which is going to be the number between 0 and 1, the likelihood or the confidence that our model has about that it's going to rain tomorrow. And we have the hidden layers. We have 2 hidden layers, and the first one, as you might have expected, contains 5 parameters, and the next one contains only 3. So these correspond to these numbers. And okay, so the thing that we're going to do next is basically I'm going to tell you about those f.relu and torch.sigmoid things. See, the thing about stacking multiple linear layers is that you will never warn any function that is non-linear. But in the real world, most of the correlations or the approximations or the functions that you want to warn are probably not non-linear. You can use linear stuff or linear approximations, but those will be just approximations. And the thing that was a bit harder to understand was how you can do neural nets and use them to warn nonlinear functions. To do that, most of the the community has gathered up and created those things called activation functions, and activation functions basically break from the linearity. So you can just go ahead and do some transformation using some activation function and get non-linear result in return. Let me explain to you what is the, for example, the ReLU function. And I'm going to go ahead and grab this code. And yeah, I'm using the ReLU in here. And the ReLU function is something actually very simple, and it's probably the most used activation function in practice. And as you can see, the values of the when you put in a value that is greater than 0, you get exactly the same value. And if you put a value that is 0 or less than this, you have just 0. So the formula for this, let me show you, is the maximum of the 0 and the number that you're putting in. So this is the sigmoid, and for the this was the ReLU, and for the sigmoid, which is again the final thing, the final function that we are applying in here, and we're using this to create our binary classifier, or to squish the numbers, the outputs between 0 and 1. So this S-shaped function in here shows you actually the shape of the sigmoid function, and the mathematical or the formula for this one is a bit more complex, but nothing too strange, I hope. So these are the activation functions that we're going to use in our model. There are more actually activation functions, more exotic ones, but most of the time you have you heard of the sigmoid, the ReLU, the tanh. If you try to use your neural network to predict whether it's going to rain or not tomorrow, the result will be pretty random, and your model should be pretty dumb at this point. So the next thing that we're going to do is actually show the model some training data and use it to teach it, and hopefully it should be a good predictor based on the data that it's seen. The process itself is called training, and it contains two main ingredients that we are going to have a look at right now. So let me just go ahead and type in the training part. The first thing that we need in here is something that tells us how good our model is currently doing. So we are going to look for some parameters. And again, those parameters are these nodes in here, and each node in here will contain some number. And our task is actually to find some numbers for each and every one of those nodes. And each number should hopefully contribute to doing some correct predictions. So the most common way for finding those parameters is to involve two components, a loss function and an optimizer. The job of the loss function is to tell you how good you're currently doing, and when this function gets to 0 or close to 0, this should tell you that your model is pretty much perfect based on the data that you have. Note that your models will probably never be 100% correct, even if your loss function is 0. And actually having a loss function of 0 on the training or even the validation or the test data is probably a sign of overfitting, something that we're not going to talk about today, but it's a real tough problem to handle in practice. So the loss function that I'm going to use today is BCA loss, and it's an abbreviation from binary cross entropy loss. The binary cross entropy loss function measures the difference between two binary vectors, which has some probability distribution. So it basically tells you how much two probability distributions differ. And again, the closer this number is to 0, the more and more likely those probability distributions are. And the binary stands for that it can only handle binary two distributions. As this is exactly our case, we want to predict, we have a binary classification or binary prediction. Is it going to rain tomorrow or not? One important thing about the BCA WOS is that expects the inputs to be based on the outputs of the sigmoid function, which we already have as in our model as the final thing that we did before returning the final value. So let's define the WOS function, and sometimes you're going to see a WOS or criterion, and this is the criteria that we're going to use for how good we are doing. And PyTorch has this BCA WOS, so nothing special in here. Okay, so after we have the WOS function that we're going to try to get to 0, we need the optimizer. And the optimizer's job is to find better and better and better parameters that drive this WOS function closer to 0. There are a lot and tons of different optimizers that are presented almost every month, I believe. And in, of course, in arXiv or somewhere in the neural network literature. But some are better than others, and some have proven to be very useful in practice and work quite well. One that is really probably the best starting point is the Adam optimizer. And the Adam optimizer is actually recommended by Andrei Karpathy in his blog post recipe for training a neural net. And the reasoning behind this is that if you are using Adam without the fluff, it's pretty safe optimizer. It doesn't blow up during training, at least not that much. And if you turn off the momentum and the other stuff, if you know what I'm talking about, the optimizer is actually doing quite okay as an initial choice. And when training neural nets, you have a lot of choices and you have to choose a lot of parameters. And starting with something as simple as Adam is probably a good first step when doing a new problem. So let's use the optimizer Adam. And this is from Torch Optim package. This optimizer accepts a lot of parameters actually, but we are going to set in only the first one, the first two actually. The first and most important parameter, or the second, I don't know, the most important parameters in here are the params, and this will be the parameters of our neural network. The next, probably still the most important parameter is the warning rate, and I'm going to put in actually the default value, but it's really good to see that we're going to use this. And the warning rate, I guess you know why we need the model parameters, because we're going to optimize those. But the warning rate, you can think of this as some sort of a trade-off between the speed that we're going to use to find those parameters, because the optimization is an iterative process, so it's doing its thing in steps, and the amount of steps that you might take might be something from between, like, let's say 100 or 1000 steps to million and probably billions of steps. And if you specify a really small warning rate, you might take just years and years and years in training before you get some good results for the parameters. But on the other hand, if you take a really small warning rate, your model might never find good parameters. Your optimizer might never find good parameters for your model. So there is, of course, more and more in-depth explanations of why this is the case, and you can Google for optimizers and gradient descent and all of the warning rate stuff, how you can find good warning rate values or initial warning rate values. But in general, again, if somebody else did some model and did the brute force steps to find good warning rates, try to start with those, or start with something as simple as the default values from your library, because yeah, the default values are probably a bit reasonable, I guess. So the optimizer is now done. Another reason why neural nets have become so popular is that they can be trained using GPUs. And training on GPUs speeds up the things by a lot. I mean, like a lot. So when you are training large models with probably millions or even billions of parameters, please do the training on the GPU. And unfortunately, the GPUs, not all GPUs were created equal when it comes to deep learning. You have to have some sort of NVIDIA GPU that is pretty recent to get some good speedups on your training. And it would be best probably to have the latest and greatest generation of GPUs that you can afford. Or you can use something like Google Co-op or maybe AWS or Google Cloud or whatever that contains GPUs that are free to use. So we're using Google Co-op and using a GPU instance in here. Just a note to have a look at what is the currently used GPU. Let me show you that you can use NVIDIA SMI. And this tells us that the current machine has a Tesla T4, which is a really good GPU. We are not going to need actually that much GPU power for this example, but still I'm going to show you how you can convert the training data and basically use it on the GPU. PyTorch makes this extremely easy actually. You just have to check if your machine has CUDA, which is the engine or the software that does most of the calculations. And then you have to basically transfer all of the data from your RAM to the GPU memory. And you can do this extremely easy using PyTorch. You just say the name of the variable to, you call this method, and you put this on the device. And we're going to do this exactly the same thing for the test. For the test. And I'm going to do exactly the same thing for the Y's. And now all of this data is on the GPU. Next thing I'm going to do is check again the NVIDIA, which will report, hopefully, some of the memory, as you can see, has already been taken by those tensors, which are on the GPU right now. And the next thing that I'm going to do is actually convert the model to the GPU as well, and the loss function. So all of this computation will be done on the GPU. And we're ready to teach our model to predict weather, or is it going to rain tomorrow. So let's start this section in here. And the training loop using PyTorch is a really simple thing to do. I'm going to just say for epoch in range, let's start with 10 epochs for now. And I'm going to predict some value using the model. Convert the prediction or squeeze the prediction, remove the extra dimension in here, and calculate the training loss using the criterion. And I'm going to pass in the predicted values and the real values in here. And I'm going to do a bit more steps after this, but let me just pause this and show you or explain to you what is the epoch. The number of epochs is going to be all of the times that we are going to show the training examples to our model. So basically we are showing our model the training data 10 times, at least for now. Okay, so we have the current predictions, we have the current training loss in here, and I'm going to print out the train loss, and I'm going to take just the value from here. And the next thing that I'm going to do is call the optimizer and call this method 0grad. And let me show you the docs for this one. Clears the gradients of all optimized tensors. So what this does is when you're using your optimizer, it's basically doing an algorithm called gradient descent. And gradient descent is trying to find better parameters for your neural net using derivatives or and gradients. And when you're doing all of this operation, those gradients accumulate, but you don't want your gradients to accumulate when you're training neural nets. So you have to zero them out or reset them. The next thing that you're going to do is to backward the loss. So this is the step that actually makes our model learn from its mistakes. So we define the forward method, and there is a method that is called backward that is defined by PyTorch. And this backward method is used to propagate the error that is the errors that our model is currently making, and hopefully help the model adjust those parameter values based on the errors that is currently doing. And the next thing that we're going to do is to ask the optimizer to do its optimization. So this is pretty minimal training loop you can do. And let's have a look at what it does for us. And as you can see, the loss is not decreasing in here. So, and as you can see, the loss is actually decreasing in here. And this is a very good thing indeed. And I'm going to basically expand this. Now that we've seen a simple training loop, I'm going to paste in the training loop that I'm using in the tutorial. And as you can see, this is a bit more complex. I'm going to let it run. And as you can see, we're going from 78% accuracy to 83.6% accuracy in here. So this model is actually learning, and these are on the training and the test set. And in here, we are having additional two functions, calculate accuracy, which basically takes the output of our model, converts it to a 0 or 1 based on a threshold of 0.5. So if it's lower than 0.5, it goes to 0, otherwise it goes to 1. And we are defining a simple method called round tensor because we want this to be a bit more prettier when printing it. And for every 100 epochs, I am just calculating the training accuracy, the test loss, and the test accuracy in here. I'm just printing those out. But the rest of the stuff is exactly the same. Now that you have a model that is performing somewhat okay, we can save this model for later. And this is pretty easy using PyTorch. We are going to define a constant model path, and it's going to be model.pointer or pth. And we're going to call PyTorch.save. I'm going to save the model, and I'm going to use the model path for that. Okay, so this is a warning that is related to Jupyter WAP or Jupyter Notebook, so it shouldn't be something that you need to worry about. And then I'm going to load the model just to make sure that everything is okay. Okay, so this runs pretty well. Now that we have our model, we need to do some evaluation and answer the basic question, is our model actually any good? And the evaluation in here, we are going to do using two simple methods. We're going to call the classification report from scikit-learn, and I'm going to show you how you can do a basic heat map or confusion matrix for this classification task. So let's start by defining the two classes that we have, which are noRain and rain. Then I'm going to take the predictions on the test data. I'm going to convert those predictions to 0 and 1 based on the threshold 0.5 and move those to the CPU. And then I'm going to get the test data to be on the CPU as well. Just to show you something, if you just take the predicted values from here and take for example, the first number, you can see that this is a number which is close to 0. If we take the next one, you see that it's again close to 0. If I take the 50th result, larger number. So we are using those numbers and converting them to 0 and 1. Okay. So I'm going to use the classification report from scikit-learn, and I'm going to pass in the test data, the predicted values, and I'm going to show the classes as target names. And this classification report is very, very good, considering how much you actually don't have to do a lot to get it. And you can see that we have the two classes in here, noRain and rain, and we have precision recall F1 score by each class. And it's really apparent that our model is very good, or at least it's good at predicting that it's not going to rain tomorrow. Based on the precision recall and the F1 score, you can pretty much say that this. And again, well, we don't have a lot of data for the training examples, and this shows pretty well in here. And this is the reason why when you have imbalanced data sets, you basically can't trust just the raw accuracy. You need to evaluate a bit deeper or dig a bit deeper, because yeah, obviously in this case, if your model says that it's going to rain, you can't really trust it. Okay, so this is the first conclusion that we did. And the next thing that I'm going to do is show you a basic confusion matrix. I'm going to paste in a lot of code in here, which makes the confusion matrix look a bit better. And yeah, we have the predicted labels in here and the true labels in here. So we have rain, no rain mistakes in here, and we have the no rain, rain mistakes in here. And again, when we don't have rain, you can see that our model is very good. But when it's raining, our model performs really bad. Basically, you can't trust it. All right, so this is pretty much our evaluation for this. You can do area under the curve or other sensitivity analysis or plotting using some thresholding and whatnot to get a better accuracy. But in general, the problem that we have in here is that we have a lot of examples for non-raining days and just comparatively very low amounts of examples for rainy days. In this final part, I'm going to show you how you can wrap your model basically in a function and how you can probably deploy your model behind an API or something else and use it to make decisions with whether or not it's going to rain tomorrow. So let's call this part making predictions. And in here, I'm going to define a function which is called WeWithRain. And it's going to take in the rainfall, the amount of rainfall, the humidity, basically the 4 features that we have. Did it rain today? And the pressure. And I'm going to convert all of this to a tensor. And I'm going to use torch.stensor. I'm going to create an array from this. Then I'm going to convert all of this to a float and move it to the GPU. Then I'm going to get the prediction of our model. And again, threshold the values at 0.5 and return the item itself. All right, so WeWithRain, if we have a rainfall of 10, I'm not sure about the quantities in here, humidity of 10, and let's say it did rain today, and the pressure was, let's say, 2. Yep, it will rain tomorrow based on this data, or this is what our model thinks. And WeWithRain, if the rainfall is 0, humidity is 1, rain today, nope, and the pressure is 100. Okay, what do you think? Our model thinks it's not going to rain. But recall that we have very imbalanced data, and based on this answer, I might be pretty sure that, I'm going to be pretty sure about this answer, but this I'm not going to trust very much. Pretty much it. You now know how you can build a neural network that can predict whether or not it's going to rain tomorrow. And this neural network is actually pretty generic. You can fiddle a bit with the outputs or the loss function and make it work on different kinds of tasks. Maybe you can try to do some regression with it or multi-class classification or something like that. I hope that you've enjoyed this video, and I'm going to be really grateful if you subscribe to this channel, like this video, or maybe write a comment below in the section. I'm going to link in the tutorial and the GitHub code and the Jupyter notebook along with it, so you can reproduce the results. Thanks for watching. Bye guys.